probably is.
So attendees are already flowing in.
How are you, Nicola? I'm in Spalding.
I'm well. How are you?
Yeah, nice to see you.
Likewise. Yeah. Last time was in Uppsala, where we were eating chocolate cake in the sunshine, like
That's correct.
with other real humans.
Tanushree, we're almost live, so be a bit cautious. Hi, Ralph.
Hello, everyone.
Hello.
Oh, it's so nice to see everyone.
Isn't it?
Nicola, the title of your talk is really inspiring. Eh?
Well, I didn't give an abstract deliberately because I thought maybe the abstract won't sound as good as the title. So.
Very nice.
But I'll try. I'll try.
I once gave a talk about world peace through DFT, so.
Okay.
Yeah.
It didn't work, did it?
I'm working on it.
Okay, I trust you, Shobana. I think you're about our last hope.
It's time, I guess.
Yeah. On dot.
Do we start? How do I know when to start? You will tell me, Nicola?
Just start. Yes, I think you can start. Yes.
Okay. Hello, everybody. Welcome to the second day of the Total Energy Workshop. I am Shobana Narasimhan from the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore, and I will be chairing the talks today. So first, we have a plenary talk by Nicola Spalding from ETH Zurich. And she has, as you can see on the screen, a rather interesting and provocative title of Finding Happiness and Saving the World Through Electronic Structure Calculations. Nicola, it's all yours, and I will remind you when you have 5 minutes left.
Okay, thanks a lot, Shobana, and thank you to the organizers, Nicola, Silke, Francesco, and Tanushree for their hard work in putting this workshop together. When Nicola first asked me to speak, he emphasized the importance of keeping our community together, even though we can't meet in person. And I very much appreciate that sentiment, particularly for our junior colleagues who you're missing out not only on the usual exchange of information in a conference, but also on this opportunity to develop your professional identities as part of this very rich electronic structure community. So I hope that we can help a little bit with that sense of identity today with this virtual workshop. And even if I can't help you with that, I hope to at least convince you that you have the computational and physics tools both to find happiness and to save the world. So I thought we should start by congratulating ourselves a little bit and reflecting on the really important technical developments that our community has made. So I made a list here of some of my favorite papers in electronic structure theory over the kind of lifetime of my generation. And I thought we could have a people's choice vote on what are our favorites. So the first two, I think everybody is very familiar with, the Hohenberg-Kohn and Kohn-Sham papers really introducing the density functional theory formalism. The second two, any of you who ever did an LDA calculation will have used these. The Seppli-Alder paper is the quantum Monte Carlo calculation of the interactive, the exchange and correlation in the interacting electron gas and the Perdue-Zunge parameterization of that. And of course, we had the wonderful opportunity yesterday to hear from Alex Zunger about his recent work. The third one, of course, Carl Paranello, molecular dynamics. And tomorrow you'll hear from Michele Paranello about his recent work. And then the last two have a little bit of a Trieste connection, since we can't actually be there today. Raffaele Resta and David Vanderbilt's development of what we now call the modern theory of polarization. So let me start a poll and give you 30 seconds. You should now see a poll, and you have the option to vote for one of these options. If you want to vote for a different paper, then you can enter it in the chat, and then maybe Shobana can track and see if you see anything interesting that we should share with everybody. Oh, this is really interesting. I can see the results coming in.
And it says host and panelists cannot vote.
Oh, okay. Oh, but we have 160 votes already, so it's enough. Okay. Yeah, pretty much what I was expecting. Some votes are still pouring in. I can't show you it till I end the poll, I think. So, okay, we're slowing down. Quick, anybody, if you want to enter. Is there anything in the chat, Shobana? Any others?
No, there isn't.
Okay, so let me end the poll, and you can see. I guess that's pretty much what I expected, that by far the favorite is the Hohenberg, Cohen, Shem papers, but the others all got, yeah, their kind of share of the votes between them. Very good. Sorry, Alex, yours. I think the youngsters don't appreciate the importance of the your parameterization of the LDA functional. Do you all see it now? Yeah. Oh, sorry. Yeah, now you see it probably. Yeah, so the in original DFT papers are clear favorites, with the others kind of sharing between them. So what I want to talk about today, though, is one that actually didn't win the People's Choice, which in my opinion is one of the great breakthroughs of the last decades in electronic structure theory and density functional theory. And that's the work by Raffaele Resta and David Vanderbilt and many other contributors on the theory of polarization. And because this is these are the papers that are really going to lead us to happiness and saving the world. So let me quickly, for the sake of all of the students, remind you of the problem that was solved in the early 90s. So back then, in kind of prehistoric times for some of you, what we didn't know was whether the polarization of a bulk periodic solid, a periodically repeating solid, was actually a bulk quantity or a surface quantity, and we didn't know how to define it. And so, of course, the polarization in a molecule, the dipole of a molecule, there's no difficulty associated with that. That if we have an isolated molecule with a negative ionic charge and a positive ionic charge, say the electronic charge E, then the dipole is just E times D, pointing from negative to positive. There's no ambiguity, there's no issue there. In a periodic solid, the intuitive way to define the polarization is the dipole per unit volume. And so if we put our molecule in a unit cell and periodically repeat it, then we could just say it's the dipole per unit cell divided by the volume per unit cell. And so we'd get the same polarization, E times D, divided by the volume of the unit cell. But of course, because our system is periodic, we have many possibilities of how we can choose the unit cell. And so let me, as an example, take this for our unit cell of size A. And now you see if we take the dipole per unit cell and divide it by the unit cell volume, we have two problems. We get that the polarization is pointing in a different direction, right? It's going from negative to positive, so now it's going to the left. And it has a different size. It's this distance now, A minus D over V. I'm going to rewrite that as E times D over V minus E times A over V. This was the polarization we got last time, and it's changed by this amount. And this thing is going to reappear. It has a special name. It's called the polarization quantum. Okay, so this was a problem. This was a problem in the late 80s, early 90s. The problem got even worse if you think about a one-dimensional chain of ions that's centrosymmetric. So here's an example. My negative and positive ions are all spaced by the same distance d. And clearly this is a non-polar chain, right? If I sit on this positive ion, I have negative ions equally spaced to either side of me. There's no dipole moment associated with this chain. But if I do the same procedure and calculate the dipole moment per unit cell, I don't get 0. I get minus E, the charge, times d over v for this unit cell, or plus E times d over v for this unit cell. And if I keep going and choose other unit cells, let's say I took a really strange looking unit cell with this cation and this anion in it, I'd find that I got always E times d over v plus some integer number of this thing we labeled before the polarization quantum, E times A over v. So this is very, very weird, right? I have a centrosymmetric chain and it's non-polar, but its polarization can never be 0 with this recipe. In fact, the polarizations, the allowed polarizations that I can make by taking different unit cells are equally spaced. I've just drawn as a cartoon some of them here. There's no 0, but what you can see is that they're centrosymmetric, right, around 0. So, so I have a centrosymmetric chain. It never has 0 for its polarization, but it has this series of polarization values, which makes a centrosymmetric set of values. And they're separated by this thing, E times the lattice constant divided by B, which we call the polarization quantum. Okay, so this was the problem that needed solving in the late 80s. And this modern theory of polarization solved these problems. And here I'm not going to derive this theory today, but I just want to write down the key results that are in those papers we looked at right at the start and which I'm going to be needing to use today. So the first thing is that the polarization of a periodic insulating solid really is a bulk property. It's not a property of the surface, it's a bulk property, but it's multi-valued. It doesn't have a single value. It's unique, but it's multi-valued. And so it's given by some amount plus n times this polarization quantum. And the polarization quantum, what it corresponds to is taking an electronic charge and displacing it by a lattice vector. And of course, in a periodic solid, that doesn't change the physics of the system because always an electronic charge comes to fill in the one that's moving that's moved because of the periodicity, but it does change the polarization by E times R divided by the volume. So this is the origin of this ambiguity. It was also a key result of this modern theory of polarization that centrosymmetric insulating periodic solids have centrosymmetric, what we call these values of polarization, the polarization lattice has a centrosymmetric series of values allowed for the polarization. And it's possible for this to contain 0, or it has to contain half a quantum. Otherwise, that's the only 2 ways you can make centrosymmetric series of numbers. And this all seemed a bit weird, except what was also noted was that differences between polarizations. So for example, the spontaneous polarization between a paraelectric centrosymmetric structure and its ferroelectric state, the measurable part of the ferroelectric polarization, these are single valued. So there was actually no ambiguity between theory and experimental reality. So I very much recommend that you go read that last set of papers on our poll at the end. And if you want a kind of easy introduction, I also have a kind of beginner's guide to the modern theory of polarization that avoids a lot of the tricky mathematics, and a YouTube series. So if you prefer to watch the movie rather than read the book, you can also work through it very at a gentle pace on YouTube. Okay, so that's the kind of little introduction for the newcomers to this area, for some of the students who might not have been familiar with this topic. Now I want to apply it to some real materials. And the material that I'm going to discuss today, I'm going to talk about just one particular polarization in one particular specific material, is a perovskite structure oxide, bismuth ferrite, bismuth iron oxide. So bismuth ferrite is multiferroic, so it has the combined property of being ferroelectric. It has a spontaneous ferroelectric polarization, a spontaneous electric dipole, and it's also magnetic. It's actually antiferromagnetic. And so its crystal structure is the perovskite structure, so it has an iron ion at the center of an octahedron of oxygens. And these iron ions are magnetic, of course. They have 5 3D electrons, so they have a very large magnetic moment. and they're antiferromagnetically coupled to each other by the usual super exchange through the oxygen. They have a little small magnetic moment because the moments cant a little bit to give a small net magnetic moment. The bismuth ions, it's 3+ trivalent bismuth, which has a very strong stereochemically active lone pair of electrons. So the bismuth shifts by a large fraction of the unit cell along the 1-1-1 direction relative to the rest of the ions. And that gives it a rather large spontaneous polarization along the 1-1-1 direction. So bismuth ferrite is very popular because of this multiferroic property, this combination of the magnetic ordering and the ferroelectric ordering, both at rather high temperature, which allows it to be used for exotic behaviors, for example, controlling the magnetism with an electric field. Bismuth ferrite is not a new material. Here's actually a rather beautiful crystal from Hans Schmidt's collection you see it's rather large, 2 centimeter across crystal of bismuth ferrite. It's very attractive. These kind of fern-shaped textures are because of twinning in the crystal. So it's a really beautiful piece of crystal, but it's of course not very good for doing ferroelectric measurements and so on. So it was with this crystal, it was not established that bismuth ferrite was a good multiferroic. And it was really only in the early 90s, and the early 2000s, when largely the group of Ramesh succeeded in growing bismuth ferrite thin film. So this is a high resolution transmission electron micrograph from Marta Rossel, who's now at IMPA. And you see here the very bright white dots are the bismuth atoms. The faint white dots are the iron. You don't see the oxygens in this image. And you see that this is a thin film, and it's very, very perfect. So one could, with such films, really do physics, do very detailed characterization. And so it was measured that there is indeed a very large spontaneous ferroelectric polarization associated with these bismuth ferrite thin films. It's 90 microcoulombs per square centimeter along the 1-1-1 direction, or perpendicular to the film direction along the 0-0-1 direction, perpendicular to the film. It's around 50 microcoulombs per square centimeter. Okay, so now with the thin films, one can really do science and engineering with the bismuth ferrite. But there's a problem when one starts working with ferroelectrics in thin films, and that's that when one has a ferroelectric polarization, when one has a polarization, then there's a charge associated with the surface perpendicular to that polarization. And one can see that rather intuitively if you think about just the units of polarization. It's dipole per unit volume, which is charge per unit area. Usually it's reported in microcoulombs per square centimeter. And so if there's a polarization of a certain 50 microcoulombs per square centimeter, that means at one end of the thin film, there's a charge on the surface of the magnitude of the same size as the polarization. And of course, it's negative on the bottom end and positive on the top end of the polarization. And this is a problem. Of course, if you have a very charged surface, it's electrostatically unstable and it's very unhappy. It doesn't want to remain in this configuration. And so this is bad news. If you want to make ferroelectric devices, usually it leads to suppression of the polarization. For example, the polarization might decide to lie in the plane of the film. It might form domains. It might screen by making electron hole excitations across the gap to make the surface metallic and screen the surface charge that way. Or it could even adopt a different phase, which is non-polar. It could go into the paraelectric state. So I want to show you where this surface charge in bismuth ferrite actually allowed us to do something positive, which was to, let me go back for just a second, to stabilize a rather interesting phase that has this property of having zero polarization. And it's a phase that's not the ground state if one doesn't have this special electrostatics, but it becomes the lowest energy phase as a result of the need to screen the surface charge. And so this is work done by Giulio Mundi, who's now at Harvard, and Bastian Grosso, who's a student in my group, and our collaborators. And let me show you first the high resolution transmission electron micrograph. This is very beautiful. So this is a heterostructure of lanthanum ferrite, which is a non-ferroelectric insulator. Then bismuth ferrite, the material of ferroelectric multiferroic that we've been discussing, and then lanthanum ferrite again. And I'll return to this point later. It's very important that it's lanthanum ferrite here. It's very important that lanthanum is a trivalent ion, just like bismuth. I'll come back to that point later. And the micrograph has been artificially colored such that the blue color is showing bismuth atoms that have shifted upwards relative to the average, and the red color is showing bismuth atoms that have shifted downwards. So normally, if this were the usual ground state, the ferroelectric ground state of bismuth ferrite, all the bismuths would have gone in the same direction, right? That would have given it the electric dipole. But here they're going up and down in pairs. And here's a blow up of, losing my mouse, sorry. A blow up of this section here, we see that 2 of the bismuths have gone up and 2 of the bismuths have gone down. And so this structure, if you just kind of count the dipoles, this structure is antipolar, right? It has dipoles, it has local dipoles. We can see that we have net displacement between the bismuths and the ions, but some of them are going in one direction and some of them are going in the other direction. So using density functional theory, Bastien Grosset was able to identify this phase. He was able to find a metastable phase, which from whichever angle we looked at it, when we compared it with the transmission electron micrographs, we saw the same patterns of the bismuths and ions. And he showed that this phase was rather low in energy relative to the ground state. It was higher in energy than the ground state, but not by very much. It was rather close in energy to the ground state phase. We call it we're allowed to call it antiferroelectric because at least in the computer, Bastien found a pathway by which he could take this phase with its opposite dipoles into a phase which was ferroelectric with the dipoles lined up. And that's a requirement for a system to be antiferroelectric, not just antipolar. The other thing that Bastien was able to show with a simple electrostatic model was that when one applies an electric field to this antiferroelectric structure, which is stable only in the heterostructure because of the electrostatic boundary conditions, when one applies an electric field of about 1,000 kilovolts per centimeter, then the ferroelectric ground state becomes more stable. So this is Bastien's calculation of the energy as a function of applied electric field. Of course, the non-polar structure doesn't care about the electric field. It doesn't change its energy, but the R3C phase comes down in energy. And this is for a heterostructure, which is why the ground state, the polar state, is initially higher in energy because of the electrostatic boundary condition. And so let me show you the measurements then. This is the measured polarization as a function of electric field. And sorry, I have to move all the thumbnails to be able to point. And you see that with no electric field, there's no polarization. But when an electric field is applied, it switches and becomes a polar structure. So this is very exciting. This is our first example of saving the world with the electronic structure calculations. Here's a schematic of all of the sustainable development goals that have been identified by the United Nations. And 2 of them are, of course, action on climate and affordable and clean energy. And usually when we think of materials for alternative energy, we think of photovoltaics, energy harvesting materials. But of course, energy storage materials where we can store off the grid, are very important too, and antiferroelectrics are very promising in this direction. Okay, but for happiness, to find happiness, there's another aspect of bismuth ferrite that we need to understand. And that comes back to this weirdness of centrosymmetric materials having polarization lattices that don't contain 0. And bismuth ferrite is actually an example of one of these. In its centrosymmetric structure, in its high symmetry perovskite structure, where the bismuth ions are not displaced, this is the structure of bismuth ferrite at very high temperature, the so-called paraelectric structure, the polarization lattice contains the half quantum. And let me just quickly demonstrate that. If I'm calculating the polarization in the 001 direction, and if I take this to be my unit cell, and these atoms to be my basis, then the positive layer from the bismuth 3 plus oxygen 2 minus is at 0, and the negative layer, which has charge minus E, is halfway along the unit cell. So my polarization, the dipole per unit volume, is minus E times A over 2V. If instead I choose my unit cell like this, then my negative layer is at 0 and my positive layer is halfway up the unit cell. My polarization is plus E times A over 2B, which is just, and if I took different unit cells, I'd get different numbers. They'd all be spaced by the polarization quantum, and this first number is half a quantum, and so on. If I put in the actual numbers, I find that half the polarization quantum is 50 microcoulombs per square centimeter. So the polarization lattice of bismuth ferrite in its centrosymmetric form contains 50 microcoulombs per square centimeter. This is the half quantum. And if you remember back to when we first discussed the polarization, the spontaneous polarization of bismuth ferrite, the magnitude in the 001 direction is also 50 microcoulombs per square centimeter. This is totally coincidence. It's just a consequence of how much the bismuth atom happens to displace. But by accident, the size of the half quantum, the size of the polarization in non-polar bismuth ferrite is equal to the size of the spontaneous polarization. And actually, this is something we knew already, although I guess I had personally not really kind of registered the implications of this in 2005 with Jeff Neaton, Claude Ederer, Umesh Wegmari, and Karen Ray, when we calculated the polarization as a function of the distortion in bismuth ferrite. Here you see the different branches of the polarization lattice. For the paraelectric undistorted phase, here are the values we just looked at, 50, minus 50, 150, and so on. And as we distorted the bismuth ferrite to its ground state ferroelectric structure, it evolved from a value of, say, minus 50 to a value of 0. The spontaneous polarization, the switchable bit, is this part here. And you see that's the same, whichever branch of the polarization lattice we go along. As I mentioned earlier, this was an important result of the modern theory of polarization. So now if I look at the polarization of ferroelectric bismuth ferrite, you see that one of the allowed values is 0. And likewise, if I switch into the other direction, one of the allowed values for the polarization of bismuth ferrite is 0. So we have this very strongly ferroelectric material, which actually can have a polarization of 0, which seems a little bit counterintuitive. The fact that the polarization, the internal polarization, cancels with the spontaneous polarization also has profound implications for the surface chemistry, though, because it means that the surface charge compensates. So if we look at the surface charge in the centrosymmetric phase, the FeO2 minus surface in the 001 direction turns out has a surface charge of minus 50 microcoulombs per square centimeter, and the bismuth oxygen plus surface has a charge of plus 50 microcoulombs per square centimeter. And I'm not going to go through the details of how one knows that this surface picks out this value from the centrosymmetric polarization lattice, but I strongly recommend this paper from Max Stengel, which details very clearly how one makes this connection. The important point I want to make is that the size of the surface charge from the half quantum in the centrosymmetric phase, by coincidence, is equal to the size of the surface charge from the spontaneous polarization. So we have a surface charge compensation in bismuth ferrite also.
Nicola, you have 5 minutes.
Perfect. I'll aim exactly for ending on time. Okay, so then we can see that we have two combinations of polarization orientation and surface termination for which the surface charge from the spontaneous polarization exactly compensates the surface charge from the half quantum of polarization. And this is what's going to bring us happiness. So here is my bismuth ferrite thin film. I've chosen bismuth oxygen at the bottom and FeO2 at the top. And so the bottom has an internal positive charge and an internal negative charge at the top. The polarization is opposite. The spontaneous polarization is negative at the bottom and positive at the top. So these cancel, and we have completely happy, electrostatically stable, compensated surfaces. There's no driving force for this bismuth ferrite thin film to form domains or to reverse its polarization. Conversely, if I try to switch the polarization, my surfaces are doubly unhappy. They have the unhappiness from the spontaneous polarization, the surface charge from the spontaneous polarization, combined with the surface charge from the internal polarization. And we can see this in the calculated density of states. This is the density of states as a function of energy, layer by layer, through my bismuth oxygen film, bismuth ferrite film. And you can see in the happy situation, there's no internal electric field. The valence band and conduction band, the Fermi energies here, are constant through the film. Whereas in the unhappy case, there's a very large internal electric field, and even at the surfaces, it becomes metallic to screen this electrostatic instability. Okay, so on happiness, we can now use this happiness and unhappiness of the bismuth ferrite surfaces to dissociate water. And this is work from Chiara Gattinoni and Ipek F.A. And so what we find is on a happy surface, again with our density functional calculations, and this will also allow us to save the world, of course, because we can generate hydrogen with this. On the happy surface, which is charge neutral, then the molecular water tends to adsorb, whereas on the unhappy surface, which is very highly charged, dissociative absorption of OH minus or H plus is strongly preferred. And so this gives us a cycle whereby if we start with happy bismuth ferrite, we adsorb water, we switch the bismuth ferrite with an electric field, and dissociative adsorption is preferred. And of course, the ions that are disfavored, then there's a strong driving force for them to leave. So for example, the H plus ions stay on the FeO2 minus surface, the OH minus ions stay on the bismuth oxygen surface. So we've split our water, and we've removed, we have a mechanism even for removing the opposite ions. When we switch back, then we're back to the happy surfaces, the charged ions leave, and we redissociate molecular water, and we can repeat this cycle. The same chemistry can also allow water remediation. This is the work of Salvador Pane from the ETH. And this is some nasty dye, rhodamin B, which is mixed with bismuth ferrite, and it breaks down to small benign molecules. And because of the multiferroic property, you can stimulate this with a magnetic field. So let me stop there. I'll skip over the analogy kind of extension to magnetic behaviors, because I want to assign for the students a homework. I give you quite some time to do this homework until the summer of 2065, because I figured you're kind of in your 20s now, that's kind of your retirement time. But you should pick one of these sustainable development goals, and with your skills and tools and capabilities, work towards solving one of them. So I've shown you a couple of examples of how electronic structure theory can help with clean water and our oceans, and also help with climate action and affordable energy, but you can pick whichever one you like. And I think you'll find that wherever you look, electronic structure theory will be able to help. So thank you for listening, and I'm happy to take any questions. I have to try and find you all on my screen. You've all disappeared. Okay, I've got you back.
Okay. Thank you, Nicola, for an excellent talk as always, and also for keeping perfect time. You have 516 participants on Zoom, as well as several on YouTube.
Hopefully not 516 questions.
No, there are only a couple. Is Marwan Alam wants to ask a question? Can you unmute yourself and ask your question?
Yes. Hello.
Hello. I don't see you. Are you there? Oh, okay, I'll just listen.
Yeah, I'm okay. I have a question about.
You can tell yourself. Maybe you can introduce yourself briefly and tell us where you're from.
Okay, I'm Marwan Alam. I am from Pakistan, and I'm a student of physics.
Okay, nice to meet you. Thank you for coming. I'm sorry, I'm not here. Are you asking your question? I don't hear you.
Yeah, can you ask your question, please? Hello? Okay, let me ask his question for you. He asked, what breakthrough can multiferroic materials make if DFT calculations help the experimental researchers who then synthesize it?
Ah, okay. So I'd say, yeah, okay. That's a good question. What comes first, the DFT calculation or the experiment? And I think in multiferroics, we have many examples where it's really kind kind of going around, right? So we first started thinking, okay, how could one make a multiferroic? And we thought, okay, bismuth could be good, and magnetic ions combining together. And actually, I remember our first DFT calculations, we proposed bismuth manganite for many good reasons, which turned out to be wrong, actually. And so then the experimentalists said, okay, that didn't work. They tried bismuth ferrite. And then we were able to, with the data I showed you, then explain why it had such a large polarization. And then, so in terms of designing new materials, I think there are many examples. In terms of functionality, also thinking about, for example, how might one, with an electric field, reorient the magnetism? That's also not so obvious, but it's something that it's perhaps easier to play with in the computer, or it's easier to characterize what's happened when you do it in the computer than it is to measure what's happened often. So also in terms of explaining and characterizing materials, I think there's very much been a back and forth between density functional calculations and experiment.
I think the question may also have been, yeah, sorry, go ahead.
How the effective is the method of DFT to calculate the multi-properties, for example, the magnetic and the electric properties at the same time. How much effective the DFT is?
Yeah, that's a very good question. So actually very standard density functional theory, it does rather good with multiferroics. They're not particularly exotic materials, right? We know that DFT is very good for electric polarization. There are magnetic insulators where, you know, bismuth ferrite is D5 ion. So it's even, you know, the gap is a huge exchange gap. And so they're not, it's ordered way above room temperature. So we don't even need to use the kind of advanced techniques that Alex Zunge talked about yesterday of trying to, the interesting physics is happening in the magnetically ordered phase. So they're actually quite simple. They're not really, they're not so strongly correlated in the exotic sense. You know, the great big classical spins, certainly for bismuth ferrite. Yeah, that's a good question. Sorry, I misunderstood.
Can Akshay Mahajan ask his question, please?
Thank you very much.
Is Akshay Mahajan there? Can you unmute yourself and ask your question? Okay, I'll ask it again. He asked, what are your views on comparison of 2D intrinsic ferroelectric materials and thin film ferroelectrics? One problem I know with 2D is out of plane ferroelectricity, ignoring experimental stuff for now.
So I'm not sure I entirely understood the question.
Yeah. Yeah. Now I can unmute. Yeah.
Okay. Go ahead. Maybe I can start sharing too, because we're looking at my slides.
1 minute. Okay. Yeah. Professor Stalin. What I was thinking. Right now, like there are many first principle calculation on 2-dimensional ferroelectrics where you have just monolayers, which could be separated from your 3-dimensional structure, like you separate graphene from graphite, like due to ancient materials. So people are like, so most of the people that I've seen right till now are their first principle calculation only, where they found intrinsic ferroelectricity within the monolayer itself. So mostly like the problem is like because within the monolayers there is a small region. So most of the time this ferroelectricity is in plane. So that is one problem. Like you have with the thin films as well. As you shown, but there are some like some people have done some 2D ferroelectrics which have out of plane. So do you have like most of the time in those papers, the reason that is given is that a critical thickness problem with this thin films of the ferroelectric. So that's why they in most of the paper which promotes this 2-dimensional ferroelectrics, they say that since there is this critical thickness problem for the ferroelectric system, this 2-dimensional ferroelectric system will be much better.
Yeah. Like, so for bismuth ferrite, these monolayers have also been made for bismuth ferrite. I don't think this characterization has been done, but from what we understand, bismuth ferrite should have a out-of-plane polarization with zero depolarizing field, right? Because of this cancellation between the surface charge from the centrosymmetric layering and the surface charge from the spontaneous polarization. So it should be stable and polar, but it should be really hard to switch because the opposite orientation is doubly unhappy than just a regular ferroelectric. So it's special in that case, in that one can make a really stable polar, very thin film with no, which is not electrostatically unstable, but it's be much, much more difficult to switch. I think for something like a regular ferroelectric that doesn't have this special property, then the polarization is always going to go in the plane, I think.
Okay. I think we have time for just one last question. So Shashi Bhushan Mishra wants to ask you a question. Can you unmute yourself and ask the question, please? Is Shashi Bhushan Mishra there? Okay, it seems like I'm having to ask all the questions today. Why on happy surface water splits, but on other it didn't dissociate?
Okay, so my naive understanding is that when you have a completely uncharged surface, then you're more likely to favor molecular adsorption, whereas if your surface is strongly charged, you're more likely to favor adsorption of charged species that are opposite in charge to the charge of the surface. That's maybe a little naive. I could also just give you the trivial answer is, we did the DFT calculations in both cases, adsorbing the molecule and the dissociated species, and we found that it was lower energy to adsorb molecular on the uncharged surface and to adsorb dissociated on the charged surface. So maybe my naive understanding is not correct.
Okay, I think we're
actually
out of time. Yeah,
is it due to electric field? Hello.
Yeah, so I think my certainly my intuition is that it's the different electrostatics surely contributes. Whether it's the only effect, I don't know.
Okay, I think we will wind up this session now. If you have further questions, I'm sure Nicola would be happy to answer them offline. I'm volunteering your services, Nicola. So we have a short break for about 8 minutes now, and then we'll come back with the rest of the talk. So you can go have a quick coffee and come back. Thank you.
Thanks a lot for your interest, everybody. Thanks, Shobana. I couldn't see the chat, so I couldn't see what people were asking. So it's great that you read them.
Yeah,
now I see
think there are a lot of them are from students starting out, I would guess. But
that's maybe nicer because they're less reluctant if you read them than if they have to interrupt. So that's really nice.
Yeah, and then there's some questions on the YouTube also about why cone sham, etc. So
Alex Zunger had a raised hand. Maybe he wanted to. Or...
Oh, I didn't see that. Well, you can chat now.
I
didn't see that. Is he there?
I think he also left for coffee.
Okay.
Yeah, I also couldn't see the raised hands.
I tried to scroll through and see if there were any raised hands, but I couldn't see them, and there are too many to keep track of. So
you think we would have sorted out this Zoom business by now, like how to? Oh. I'm still on my tiny laptop. I'm like holding out buying a big screen for home because I keep thinking we've got to get back to the office soon, So I'm on this tiny little laptop screen. Oh, hello, Max. You just popped up in a square.
Nicola, good to see you.
Hi, Max. Hi, Max.
Shall we try to share screen with the speakers?
Yeah, so is Madil Mustafa there?
Yes, I'm here.
Am I saying your name right?
Hadil.
Oh, it's Hadil. Yeah, is Hadil Mustafa? Yeah. Am I saying it correctly?
Yes.
So that we're seeing it in your presenter's view. So can you go to the full screen view? We're still seeing we're seeing it in the editing mode.
I will stop sharing and do it again. Your screen. What about?
No, just make it full screen.
Yeah, okay.
You know, at the bottom, yeah, you click on, yeah, now it's fine.
Yeah, it's fine.
Okay. So, and maybe I'll check with the next person, Ibanez Asperos.
Yeah,
Are you
it's
there?
me. Can you hear me?
Can you tell me how to say your name?
It's Julen, and
It's-
the surname's well, Ibanez Aspiros. But if it's too complicated, Julen, it's enough.
Oh, that isn't there on the program. So how is that spelled?
The name, Julen.
Yulen.
Exactly.
Okay, all right. Yulen Ibanez
Should I
Asperos.
try
Okay.
to share my screen?
Yes, please. Hadil Mustafa, can you stop sharing, please?
Yes.
Okay, so I'll share the screen. What?
Yeah, looks fine. Perfect.
Okay. Well, just in case, before I start speaking, I will ask whether you hear me, and I will.
Yeah, of course.
Yes, and then I will start speaking.
Yeah.
Okay. Thank you.
And Kitano, are you there?
Yes. Let me try to share my screen, Shobana.
Yeah.
Yeah.
You need to go full screen.
Is it?
Yeah, that's fine.
Great.
And George Dangic?
Hi. Yeah.
Am I saying your name correctly?
Yeah, it's perfect.
Okay.
I will try
Can you
sharing.
try to share? Yeah.
Do you see it in full screen mode?
Yes, I do.
Okay. Thank you.
Okay, so each of you have 18 minutes for your talk and 3 minutes for questions. How many minutes before the end would you like me to give you a warning? 3 minutes or 5 minutes, or what would be good?
5 minutes is good, but I think that I will finish before the 18 minutes.
Okay, all right. So I'll tell you when you'll have 5 minutes left.
Okay.
So we'll start in another minute. So you can already start sharing your screen, yeah. You still need to go full screen. Yeah, that's fine. No, now it's not okay.
Oh, okay.
Yeah, this is okay. Do you want to just try changing your slides just to check that that works?
Yeah.
Yeah, that's okay. So you can go back to your previous slide. Okay. So we'll start with the shorter talks now. So the first talk is by Hadil Mustafa from the Technical University of Denmark. And she will talk about investigation of one-dimensional materials. And I just want to remind all of you that if you have questions for the talk, because it's a bit hard for me to keep track of raised hands when there's so many participants, it would be good if you just type your questions into the chat box. Please go ahead.
So thank you for the presentation, and thanks for organizer. And finally, thank you for having me here. So I'm trying to make a database for my one-dimensional materials with their calculated properties. So if we take a look on one of the materials, it will look like that. So here I have the 1D component and some structure information. And here I have all the calculated properties, the thermodynamical stability, the phonons, the basic electronic properties, the band structure calculated using PBE, the effective masses, the band structure calculated using HSE, and finally an overview over all the items that have been calculated. So what is a one-dimensional material? A material is said to be one-dimensional if it's periodic in one direction and has limited extension in other directions. So it's a chain of atoms. One-dimensional materials are interesting subset of materials with promising application in different fields. And here I have 3 different examples. In the first one, the 1D component is titanium sulfur with chains, which has been used as a transistor. And in the second one, the 1D component is tantalum selenide, which has been used for application as a small nanowire and interconnect. And the last examples is a more complicated structure of the 1D component, which has a core in the center that are electrically conductive. So for the identification of one-dimensional materials, all the work has been done by Peter Larsen, where he made a screening that applied for the inorganic crystal structure database and the crystallographic database, where the dimensionality of a material is determined based on the interatomic distances. And he defined a scoring parameter in order to identify all the low dimensionality materials. So 2 materials, I and J, are bonded if the distance between them are less than the sum of the covalent radius multiplied by a parameter called K. So K is considered as a continuous variable, and that's why they can define a scoring parameter. And the dimension of a component can be determined as the rank of the subspace of the atoms and its connected neighbors. So after that, we estimate the dimensionality by using different value of K. So at the low value of K, no bond exists between the atoms, and then we are only dealing with the atoms itself, and then it's 0-dimensional materials. And then when K increased, then the bond begins to set up between the atoms, and then at a certain value of K, K1, then we have a 1D component that appear, and then when K increased to K2, then the 1D component disappear, and then we have a 2 or a 3D component. So if we take an example here and look at the boron nitride, then at low value of K, then we have a 0-dimensional materials. Then at K1, the covalent bond begins to set up between the atoms, and then we are dealing with a 2D materials. And then at K2, then the red line appear between the layers, and then we are dealing with a 3D component. So here we see a plot for all the structure in ICSD and COD colored according to their dimensionalities. And here we have all the one-dimensional materials. This plot is when we are looking at one-dimensional materials, and it's characterized by a high value of K2 minus K1 and a value of K1 not much larger than 1. And the black line here is the scoring parameter at 0.5. The K2 minus K1 shows also our width of the range. And here we have examples of different dimensionality materials, both the low dimensional materials 1 and 2 and 3, and some mixed dimensionality 1 and 2 and 1 and 3 with a high scoring parameter for all of them. So from now, we will deal with the one-dimensional materials. So all the materials that are from ICSD and COD can be found in the CMR database, which stands for Computational Material Repository. And this is our initial database that we will use to find our one-dimensional materials. And for that, we have some criteria. First of all, that the 1D scoring parameter is larger than all the other scoring parameters, both the low dimensional is 2 and is 3, and also the mixed dimensionality scoring parameters, that the unit cell include up to 80 atoms and up to 4 different chemical elements, and the 1D component include up to 20 atoms, and we removed by hand all the materials that has some issues, be missing atoms or invalid structure like theoretical structure or partial structure, and then we end up having 287 materials, which what we will call for our core materials. So for those core materials, we make a geometry classification by calculating the mean square distance between 2 one-dimensional systems. And for that, we take into account that we ignore the chemical identity of the atoms and only look at the coordinates. The two materials may include different numbers of atoms, and for that we multiply both of them with the lowest multiple of atoms, and finally rotating and scaling the unit cell along the materials. And here we have our illustration of the root mean square distance, where the cluster of similar materials are lying at the diagonal. After that, we make a distribution of our distance matrix, where the y-axis is the number of the considered structure, and the peak at 0 are represented the diagonal at the distance matrix. And as we also can see that we are dealing with two parts. The first part where the material are close to each other and where they are far away from each other. For that, it makes sense to make a separation, and we did that at 0.75 angstrom. We make a further analysis by looking at the single linkage clustering, which is characterized as a function of the cutoff distance, which is 0.75. And from that, we got 48 groups. 27 of them contains 3 materials or more, and 13 groups have 5 materials or more. And here we have the materials that have 5 or more. And as we can see, some of the materials are characterized according to the grouping in the periodic table. As we can see here, we have zirconium iodide, zirconium bromide, and zirconium chloride. As we also can see that we have in the first group 2 zirconium iodide, which is because that they are expanded from 2 different 3D materials. So now we want to extract our database by making some element substitution. And in this paper, they introduce a probability measure, which shows the probability of getting a new stable material when we make a substitution from an element A to an element B, which are shown by the dark color here. And in our case, we make an element substitution from A to B with a probability measure that is larger than 0.2. And here is all our substitution that we did. And we get 565 new structures, which is our shell materials. So for both the core and the shell materials, here is our computational workflow, which has 2 parts. The first part is the structure and the stability, and the second part is the properties. For the structure and the stability, we start by making a relaxation of the cell and the atoms in all the magnetic state. And here we see the magnetic state for the core materials. As we can see, almost all of them are non-magnetic, and some of them are ferromagnetic, and a few of them are antiferromagnetic. For the shell materials, almost all of them again are non-magnetic, but now more of the materials are antiferromagnetic compared to the ferromagnetic. We looked at the dynamical stability and the thermodynamical stability. For the properties, we calculate the balance structure using PBE and HSE. We calculate the density of state, the work function, and the effective masses. The workflow is managed using atomic simulation environment and atomic simulation repository. So we also looked at how stable is our one-dimensional materials by comparing the energy between the 1D and its extracted 3D component. So for that, we make a new calculation where we use the same computational details as in the relaxation, but now instead of using PBE as the exchange correlational functional, we use PBE3. And as we can see, almost all of them are ranging a bit over 0, which shows that they are slightly unstable. And because of that, we can still extract the 1D from the 3D and calculate their properties. Some of the materials are having a negative value, which means that when we extract the 1D from the 3D, we gain some energy, and which means that the 3D are unstable. And these three values are probably wrong, but our calculation are running automatically, and something wrong might happen. For the materials that are lying here, that means that the 1D are unstable and the 3D are more stable, that it's hard to extract the 1D from the 3D. We did the same for the shell materials, and as we can see, almost all of them are also lying a bit above 0, and we have some outliers here.
Excuse me, you have 5 minutes left.
Yeah, okay. Which shows that we have been lucky with our choices, as almost all of them are good enough to be done. So for the dynamical stability, the first thing we do when we look at the material is the relaxation. We calculate the relaxation, but as the relaxation only shows that we are on a saddle point, we calculated the dynamical stability, which is the phonon in the cell. And for that, we calculated the forces, which represent the curvature of the potential energy surface. And if the principal curvature is negative, then the structure is unstable. And here I have two materials. This one is stable and this one is unstable. And here we have the three translation mode. For the thermodynamical stability, the convex hull is constructed in the enthalpy space. And as we can see, the blue line is the convex hull, and the blue point here are the bulk references structure, which are all from the OCMD. And the orange point here are our 1D component. So all the materials that are lying at the convex hull are stable, which means that this one is unstable. And we also looked at the energy difference between the 1D and 3D for the convex hull. And as we also can see, for both the core and the shell, almost all of them are good enough to be done. And we have some outliers again. So for the properties, we are currently investigating some properties, but here I have the band gap energy. As we can see, for the materials that are lying at 0, they are metallic, and the materials that are lying between 1 and 2, they can be interesting for some light absorption. So the conclusion is that we have begun a systematic study of one-dimensional materials using DFT. The materials are classified based on the root mean square distance. We obtained the atomic geometry and other properties like the convex hull and the band structure. We are working on investigating some properties, and other 1D database can be found in the work from Ivan Reed. And I also know that Nikolai Massari's group are also working with the 1D materials and Henny. Yeah, that's it. Thank you.
Thank you very much. Are there any questions? Let me look there on the chat. Okay, so Singaravelan has a question. Can you unmute yourself and ask the question? Okay,
Hello.
Yeah, please, can you ask your question?
Just I want to know about that convex hull.
Yeah.
What do you want to know about it? Can you just make your question more specific? What do you want to know about it?
Actually, you told about the formation energy, right?
Yeah.
Then what's the relation between this convex hull and the formation energy, or both are same?
So the energy above the convex hull is our formation energy, and the materials that are lying at the convex hull are the materials that are.
Is the question about why one plots a convex hull and what it is used for?
Yes.
Is that your question?
Yes, that is my question.
So maybe you can explain to him about why you plot a convex hull to look for phase segregation, etc.
Okay, so why I plot the convex hull? Just in order to be sure that our material are stable. So the thermodynamical stability shows how stable our material is, and to be sure that our material is stable. So the relaxation only shows that we are on a settle point, and on a settle point, and that's not enough to be sure that our material is stable or not.
Okay.
Okay, thank you. I can explain to you more if you write to me, but basically when you have something with many constituents, you can plot a picture like this, and if it doesn't lie on a convex hull, it will phase segregate into other constituents, okay?
Okay.
Who else? Syed Wahid Hosseini says he has a question. Do you want to ask? Syed,
Me?
yeah.
Can you hear me?
Yeah.
Thank you very much for your nice talk. This is Baid from University of Tehran, Iran. I'm going to ask you about the machine learning technique. What features did you consider for learning these things?
So I actually...
You talked about the distance of the atoms, is it enough, for this, for dimensionality analysis?
Did you use any machine learning?
Yes.
I used a code that is done by one in the group in order to extract the new raw materials. So I didn't do it by myself.
Okay. Thank you very much.
Okay, I have a question, if I may. I was wondering why you chose to start from 3D materials. I mean, I naively would think that the structures of 1D materials would be quite different from that of the corresponding 3D material. And so is it useful to start from the 3D material? Or is it typically that it looks like a part of the 3D material that's been pulled out because you have chosen materials which have essentially 1D-like character in 3D also?
We only choose we looked at the 1D materials that are extracted from a 3D materials that look almost like a 1D. So it's a chains of atoms. So that's why we can extract the 1D from it.
Okay. I think we are out of time. Thank you very much again. Can you stop sharing your screen, please? So the next talk is by Yulen Ibanez Asperoz from the Materials Physics Center in Spain. Can you share your screen, please?
Yes, I will share now. So can you hear me fine and see fine?
Yes, it's excellent. And he will talk about ab-initio calculation of the shift photocurrent by one-year interpolation. Please go ahead.
Okay, thank you very much, and hello everyone. So today I will talk about the shift current, which is an effect that is a particular contribution to the bulk photovoltaic effect, which is a more general effect, although often both terms are used interchangeably. Now, this consists of a nonlinear light absorption process that takes place in non-centrosymmetric crystals. That is, the material must break inversion symmetry in order to show this effect. Very large photovoltages above the band gap value can be attained in this effect, and it was largely studied during the 70s and 80s, but we find renewed interest today. Now, one of the main characteristics of this effect is that it can conduct a photocurrent in an homogeneous material. If we think of usual photovoltaics, one needs an interface like a PN junction in order to generate an internal electric field that will drive the photoexcited electrons. But in a bulk photovoltaic, this is done automatically by the material. So the role of the interface, in some sense, is done now by the broken inversion symmetry of the material that allows to conduct electrons along certain directions. A simple or intuitive point of view or the physics to understand this is to think that every time the electron absorbs a photon, it changes its energy, but also it changes its position within the unit cell. Or to be more strict, the real space center of the bands are displaced or shifted upon the photoexcitation. That's why it's called a shift current. So when the material absorbs light, in average, electrons end up moving in a certain direction, and therefore they generate a photocurrent. Now, as said, this effect was measured some time ago. Here we have a typical example, a typical spectrum. We have the photovoltage in the y-axis and the wavelength of light in the x-axis. And besides, well, this was measured in ferroelectric barium titanate, which is a prototypical bulk photovoltaic. And besides the large value of the photovoltage, there is one important thing to notice here, and it's that for different polarization of the light, one can attain photovoltages that have opposite sign. That is, current will flow in opposite directions depending on the polarization of light. And even more, if we restrict to a given polarization, the sign can change as a function of frequency. So in this sense, it's an effect that has a large degree of freedom. Now, the recent interest is motivated because the bulk photovoltaic effect and more generally nonlinear optical effects seem to be closely related to some fundamental properties of materials like topology. For instance, in the work in the upper panel, this is a density functional theory work that showed that the shift current experiences a sudden change of sign when the topological phase boundary is crossed. So it's very sensitive to the topology of the system. Another line of recent research that has been pushed forward recently is that of two-dimensional materials. Again, the upper work is a density functional theory work where very large shift current photoconductivities were predicted in single layer monochalcogenates. So here we see that the photoconductivity reaches up to 100 microampere per volt square, whereas the typical bulk values are of order 10. So there is an order of magnitude enhancement when the dimensionality is reduced to 2 dimensions. And this was mainly ascribed to the strong Van Hoff singularities of the density of states in 2D. Recently, there have been a lot of interesting results in the field of bulk photovoltaics and nonlinear optical effects. This is a short survey of those for the interested audience. And well, this was the introduction up to here of the shift current. And from now on, I will focus mainly on 2 points. One will be the approach, a theoretical formalism for the calculation of the shift photocurrent using Van interpolation, and then I will show the applications of the method. First in gallium arsenide, which will serve as a benchmark system, and then in a more interesting system, graphite B-C2N, which will serve to discuss dipole selection rules. So, as a warm-up, and before going to the nonlinear response, let's remind how the standard linear case looks like. We will work in the single particle case. Now, in the standard response, the current is proportional linearly to the electric field of light. Here, A would be the direction along which the current flows, and the relationship between the two quantities is given by the photoconductivity, the optical photoconductivity. Expression of this quantity is written here. N and M are band indexes, the Fs are occupation factors, and the delta takes care of energy conservation. Now, the important bit is in the transition matrix elements. And in this case, these matrix elements are those of the position operator. Why does position appear here? Well, we can think that if we describe the light in length gauge, then the electric field of light will couple to the position operator of the electron, and that's why we need to take matrix elements of the position operator in order to describe the response. So for practical calculations, one has to calculate what's called the dipole term. It's also known as the Berry connection. And for this, one needs to compute k-space derivatives of the Bloch function. Now, if we go one step further and now analyze the shift current response, this is a second order DC current response. In this case, the photoconductivity is different. This one transforms like the piezoelectric tensor, and its expression is shown here. Now, we still have the dipole on one hand in transition matrix elements, but now we have a new term that is not present in the linear case, which is the generalized derivative written here. And this generalized derivative contains, among other terms, a k-space derivative of the whole dipole term. And this is a troublesome quantity to calculate because of the k-space phase indeterminacy of Bloch states. So the main challenge resides in computing this term for an accurate description of the shift current. In the literature, there have been a number of proposals. A popular one adopted by the group of Andrew Grab and among others, it's been to use discretized expressions for the derivatives using finite difference formulas. And this approach is very suitable for regular k-space grids that are commonly used in density functional theory calculations. Now, this technique has been successfully applied to a number of materials. Here on the right, we show barium titanate, where the theory matches very well the experimental values, and even the trends are well reproduced. But on the other hand, this scheme can become computationally heavy, as it needs many k-points for first principle. Each wave function needs to be calculated by ab-initio methods at each k-point. So if we want to study systems where we need a lot of k-points, like 2D systems or even biosemi-metals, then we need this would become computationally heavy. So that's why we have considered an alternative strategy, which is to consider Van interpolation. Now, broadly speaking, in the Vanier formalism, one needs to consider a finite energy window where one wants to describe properties like the shift current spectrum. So then, if one follows the Vanier procedure, one can end up Vanier interpolating several quantities within this window. And this can be the band structure. This is a well-known example, but not only. One can also interpolate transition matrix elements, and that's our aim. That's where we have worked. We have tried to express the shift current transition matrix elements, and more specifically the generalized derivative, in terms of Vanier functions, in the Vanier function language. Now, as a quick reminder, Vanier functions, which are denoted by lattice vector R, they live in real space because they are given by a Fourier transform of the Bloch functions from reciprocal to real space. And here they use our unitary matrices that mix bands. So in this sense, because of this real space structure, the Vanier formalism is very close to the tight binding formalism, actually. Now, then it all consists on plugging this expression into the matrix elements and start collecting terms. There are many terms that appear, but at the end of the day, in Vanier formalism, all of them can be calculated from just two matrix elements in Vanier basis. One is the matrix elements of the Hamiltonian in Vanier basis. For an analogy with tight binding, this would be the on-site and hoping terms, and this fully describe the energetics of the problem. For instance, they are enough to give the energy spectrum. But we also have matrix elements of the position operator, and this is perhaps a bit less familiar, since again, if we think of tight binding, in tight binding, position is diagonal. The position enters only, it just marks where the orbitals will sit. But in Vanier formalism, we have the full of diagonal structure of the position operator in real space. In that sense, it's a sort of exact tight binding model. And as we will see, this description will be important in capturing the shift undergone by the electron when it's photoexcited. But before that, let me just point the main advantages of this method, and mainly point that it allows an efficient calculation of the shift current, of the shift photoconductivity, thanks to Vanier interpolation. Up to 1 million K points are easily feasible, which reduces the computational time heavily. And let me also mention that this formalism is now implemented into the latest version of the Vanier 90 program, and work is on the way to have it implemented into the Python Vanier Vericode 2. So with this, I will show now results for gallium arsenide, which will then serve as a benchmark for the method. Now, in this upper panel, I'm showing the shift photoconductivity for the only component that is allowed by symmetry in this material. And I'm comparing our results with results available in the literature. Now, the comparison is good, but for reference here, I included also the calculation of the linear response. And we see that the agreement between the two results is very similar in both cases, which makes us be confident about the method. Let me also note that the peak structure of both response functions is very similar, and it's actually related to the underlying joint density of states and its peak structure. So the test is passed, but we can use now the Vanier formalism to learn more about the problem, of the physics that are underlying. And how can we do that? Well, we can, because of the formalism, we can switch manually off the diagonal matrix elements of the position operator. We can refer to this as the diagonal tight binding approximation, because in tight binding, those terms are not considered. So the result of doing so is shown in blue. So for the linear response, we see that it doesn't do much. So this means that those terms are not important for the linear response. So this approximation is good for the linear response, but not for
excuse me, you have 5 minutes left.
Thank you very much. So it does it does have a big impact on the shift current spectrum because it induces a relative error of approximately 50%. So for the numerics, these of diagonal position matrix elements are important for the shift current, and even more, they are a quantitative proof of the strong wave function sensitivity of this particular response. So, and in the remaining of the talk, I would like to now focus in the next material and more interesting system that is a second application of the method. And this is a graphitic bismuth. So this material is a layered semiconductor that has a broken inversion symmetry. Because of its structure, it contains weakly coupled layers, and we can expect a quasi-2D properties that will, again, we can expect a large shift current response. Now, the most important physics happen close to the bandage. Here in the upper panel, we show the band structure, and in the lower panel, the direct band gap. So the bandage lies somewhere between the S and X points, here pointed by the red dot, and the direct minimum band gap is 1.2 eV. Note also that there is a saddle point at the X point at 1.3 eV approximately. So we can say that the bandage region lies between these two energies. Now, we have applied our formalism for calculating the shift current, and we show here the two conductivity components that are allowed by point group symmetry, YYY and YXX. So the first one is fairly small.
Hello?
Yes. The first one is fairly small, while the other one starts to grow right at the from the bandage and reaches a maximum at 1.3, around 1.3. Now, this value is very large. It's actually, this magnitude is among the largest bulk values reported in the literature and peaks in a suitable energy range for some potential applications. So in this sense, this material can be interesting. But that's about the size. But what about the direction of the current? Now, these two components allowed by symmetry correspond to quite different setups. In one of them, current flows parallel to the electric field of light. This is usually the most common setup. But in the other one, it flows perpendicular to the field. And if we focus on the bandage region in the gray area, we notice that only the perpendicular component is finite. The parallel one is completely vanishes. So why is this? Why does it vanish even though it's allowed by symmetry? So this actually can be traced back to a quantum dipole selection rule associated with mirror eigenvalues, as we will show next. Indeed, the crystal structure has a mirror reflection. It is mirror symmetric in the X coordinate. So now, because the bandage lies actually at a mirror invariant point, the SX line is a mirror invariant line, and the bandage lies there, then this means that the bandage states have definite mirror parity. And this parity can take on two possible values, plus or minus. In the case of BC2N, valence and conduction bands, shown here, have opposite parities. So let's keep this in mind and consider now the expression for the shift current matrix element, and more in particular, the dipole term. So one can distinguish two dipole selection rules depending on the relative parity of conduction and valence bands. When states have the same parity, the matrix elements containing the mirror index is forced to vanish. That is, the dipole term Rx is forced to vanish. Whereas if the states have opposite parity, then the matrix elements without the mirror index, in this case Ry, is the one that vanishes. And what does this mean in practice? Well, combining this with the shift current expression, dipole selection rules imply that in one case, the current can only flow parallel to the field, while in the second case, the current must flow perpendicular. And the first situation actually is what takes place in monolayer germanium sulfate, and this is shown as in retrospective, which was analyzed in these two works. And the second situation that we have shown, it's actually taking place in BC2N. So the interested audience can look for more information here if interested. And with this, with acknowledgements to the people that has been involved in this work, Ivo Sousa, Stepan Cirkin, and Fernando de Juan, and thanking funding, I would like to finish. Thank you.
Thank you for a very interesting talk. We do have some online questions. We may not have time for all of them. Babu Brejnath Prasad, would you like to ask your question?
Hello, am I audible?
Yes.
Yeah, thank you, Professor Julian, for the nice talk. I have a question, which is that if the spin orbit coupling is necessary for doing the shift current calculations.
Mm-hmm. Good question. So it's not a key player because, well, the results I have shown are for semiconductors with a big band gap. Spin orbit coupling here wouldn't play much of a role. It's not like some effect like anomalous Hall effect where spin orbit coupling can be key, but here the physics are not dictated by spin orbit coupling. They can be in recently interested materials for nonlinear phenomena like biosemimetals, where the band gap is smaller and then spin orbit coupling will have bigger effects.
Oh, okay, thank you. And how about the seizure shifts? Because since we are dealing with semiconductors, we might need to have a accurate gap to have a good spectrum of shift current.
Totally true. The good thing is that the shift current, the matrix elements, and the whole conductivity is invariant under the assessor shift. So it will just shift the spectrum, the calculated spectrum, to higher energies usually, but the profile of the spectrum would be the same. It's invariant.
Oh, I see. Thank you. Thank you so much.
Syed Wahid Hosseini, can you ask your question briefly, because we're sort of running out of time?
Can you, sorry. Thank you very much for your nice talk. I have a question about slide 17. In slide 17, yes, there are some peaks on the diagram. Could you tell me the physical meaning of these peaks or not? Because in imaginary dielectric function, we know that the peak shows the absorption, but for current shift, what is the meaning of these peaks? Thank you very much.
It could be a similar meaning. So as said, both the linear and the shift current response show the same peak structure, and the origin is actually the joint density of states. So where bands show more or less parallel dispersion, when you have two bands that are connected at that energy and have sort of parallel dispersion, you will have a big peak in the joint density of states, and this will also be shown in the shift current.
Thank you.
Okay, thank you very much for your nice talk. I think we have to move on now to the next talk. So can you stop sharing your screen, please? So the next talk is by Caetano Rodriguez Miranda. Can you make it full screen, Caetano? Yeah. Okay, so this is Caetano Rodriguez Miranda from the University of Sao Paulo in Brazil. And he will talk about materials discovery for biomedical applications, from machine learning and first principles calculations to finite elements.
Thank you very much, Shovana, for your kind introduction. I hope that is everyone well, and I actually would like to be in my beloved Trieste to have a narrow in the ICTP cafeteria. So I'd like to thank the organizers for this incredible opportunity to give this talk in the Total Energy online. And it's very interesting to share this work that has been a combination of expertises like the materials engineering, the chemistry, mechanical engineering, and a physicist, towards the proof of concept to use materials discovery for biomedical applications. Now, the seminar is actually all about the use of a combination of multiphysics and a multi-scale approach. We're going to try to figure out biomedical applications where you're going to use machine learning together with first principle calculations in order to check and verify the properties of the systems, and basically try to end the cycle through looking for real applications. So you're going to see how these electrical properties is really works on a bond, for instance. Now, the motivation is looking for the structural biomaterials and bioimplants. You are very much interested in that because of the use. So you have this interface between the bond and the implant, and this requires several the right combination of the density as well the elastic properties of that in order to avoid the bone stress shield effect. Now, in the case of the bone, this is very complex material. In this interface between the metallic implant with the bone, you have several challenges here. So one of them is that you have a very rigid part, the external part of the bone, but also have a low modulus region that is actually with the soft part and where you have the blood and other bioactive sense happening. So what you're trying to see is how can you look for materials that have the right combination where you can use it, for instance, in bioimplants, and also to avoid fracture, and particularly you have a huge pain in case of you have this disbalance between those materials. So this has been motivated because in Brazil, this is actually a huge market. You were talking about something of the order of $4 billion a year that you lose because you are not able to have those materials or those systems to use ourselves. In this, with the population aging, is this supposed to have even more needs with this kind of systems. Now, of course, you have already several options in place. The most of them is related to titanium, metallic titanium, where the current best one is the so-called the gunmetal, where you have the TNZT alloy. Here you have a very good combination between the low elastic modulus, the good biocompatibility, high strength, but the problem is the high cost of it. So you are looking for, particularly here, materials that have low cost, but you still have a good balance between the yield strain and the moduli, particularly looking for the elastic absorbable strain with respect to the cost. So this family of systems is here, and you try to look into something that is more at low cost, but still have the good properties from in the biocompatibility. Now, the first thing that you have to do is to look for the periodic table for the bio implants. And basically here you have the metallic systems. This is the elements on it. And looking for the biocompatibility of that, and there are several other properties that you have to look for. In this particular case, you search only for the green ones. That is for us, it will be you could avoid any problem for the biocompatibility. And then requires the titanium, zirconia, and niobium. But of course, you have the ruthenium, but the ruthenium is better to use for catalysis. And also, you have a very high cost on that. Now, in this way, you are looking for alloys that have this combination, titanium, niobium, zirconia, and you hope that the elastic properties can reach those this region, in particularly low cost. But the problem is what would be the composition of that. Now, to do that, one strategy is that people use a lot on the material discovery. Now, it's still a very try and error. So, but the problem here is that you have a multi-dimensional optimization problem that you have to look for which is the best composition for a given system. However, most of the time, the parameters and the properties are unknown. So you have to look for that. And the one way is to only search for the best candidate. So in this way, you can synthesize, characterize, and test it is in the way that you can save a lot of time and also cost. So the approach that you're going to use is actually back in time in terms of the evolution of the methodologies from the scientific point of view. You're going to use the machine learning methods in order to make a selection of potential candidates. Then you validate it with this functional theory. Then you're going to use the linear elasticity to see for real applications before doing actually the experiments on this system. Now, the methodology that you have used is a combination of multiphysics and multi-scale methodologies that you want to narrow down the possibilities in order to apply for a real system. So in this way, we start with databases. In particular, here you have used the materials project. And remember that one thing that has motivated us a lot on this work is that because in Brazil, 8% of the NIOB is here, and could be something that could be used for from the economical point of view. Now, you have used machine learning methods in order to get information of the electrical properties based on composition. This was some of the packages and also libraries that you have used. With that, you select some of the materials and you test it with the dense functional theory. When here, particularly, you have a problem that you have to use the special quasi structures in order to approach the alloy problems. Now, this information that comes from the this functional theory then is used to feed the elastic properties, where you perform some finite element simulations. You could see if the alloys and systems that you search is in a good shape to be used in real conditions and also for real applications. Now, how has been done these several steps under the way to reach the full alloy and the material itself. So we start with the composition structure, as has been seen in several of the talks today. So you narrow down the possibilities, looking only for the transition, post-transition metals. This gives to you this amount of entries. Now you filter out even more. You excluded any ionic or covalent character of those systems. Then you look also for electrical properties in the range of titanium alloys. That is interesting for us. And finally, the information that comes from the heat formation in the entropy mixing. So this gives to us around 2,000 entries. Now, what you are looking for is to be able to predict the elastic properties based only on composition. So using this machine learning process. So in this way, one important step is to look for, in the exploratory part of the machine learning process, is to look for which features will be potentially the best in order to describe a given target property. So to do that, you do a feature selection. So you could figure out what is the best features that can somehow let us have a model based on the only based on composition. And finally, this has been fed some linear models or random Florestal regressors in order to be able to train a model towards the book modulus or the shear modulus, again, using only the composition information. So this was more or less the step regarding to the machine learning process. Now, just to give you an idea about this has been done for the shear modulus. Here you have you explore several options. One is linear regression or random forest, as well the neural networks with the full descriptors and select a number of descriptors. So based on that, you could see that the database compared with the predictor in our model, in particular for the random forest, is quite interesting. And also have a very small error compared with the other system. Now, you have been able, with this model, to apply a selective one. Here you use the Keras library in order to have this information. And then you are able to get what is the best features that somehow can capture the elastic moduli using basically using the composition. Now, in this particular case, for the shear modulus, you end up with the Poisson ratio to be the most representative one. Of course, you have other ones that I can comment later on. But somehow, with this information, then you are able to get the phase diagram, the titanium, zirconia, and niobium, using this moduli, using only the composition information to get information from the elastic point of view. So in this particular case, I'm showing the Poisson ratio that is somehow related with the mixing entropy. And you could make the correlation between what is this machine learning models is given to us together with the physics behind those systems. Now, this is very interesting. So you could do then they calculated the elastic moduli. This is what you see as the machine learning prediction using two completely different methods, the random forest and the neural networks. And we end up with a very interesting sweet spot here, on where you have a large concentration of titanium, and then you also have the combination of zirconia and niobium. So this could be seen in both methodologies, in both models. In this, this was the map for us to look for those compositions in order to see if you can end up with a material with a low moduli, that elastic moduli that can be applied on bio implants and bio applications. Now, however, I have to remind you that this machine learning predictions is only based on composition, means that it's agnostic to the structure. So this is where you have to use the first principle calculations, for instance, in order to understand and validate if those compositions are really stable, and also can be used as a good material for bioimplants and biostructures. So this is more or less what you have done. So for this under the sweet spot on this composition, then you look based on first principle calculation about the phase diagram. And here I show to you the phase diagram of titanium with pressure and temperature, because you have to look for if the structure that you are looking for is really the one that can be stable for a given situation. In this particular case, since titanium is the largest amount in alloy, you are looking for the beta phase, that is the low modulus ones, that is the BCC phase. In particular here, you have to avoid 2 points. One is the transition between the low temperature phase, the alpha to beta. And also, if you cool it slowly enough, then you can reach this region, that is the one that you would like to go. And finally, if you do a fast cooling, then you may end up on the omega phase. So this is a problem.
Gaetano, you have 5 minutes left.
Great, yeah. So then you figure out here you get a phase that have a higher moduli. So you have to understand from the thermodynamic point of view, from the elastic point of view, what is going on. So then you have done a series of calculations based on this functional theory to see how is the stability of both phases, the omega and the beta, and also the beta with respect to the alpha one. Now, because of the time, let me just quickly show to you what you have end up. So you look for the influence of the zirconium, then you keep it fixed, this content. Then you change the amount of niobium, because the niobium stabilize the beta phase in titanium. So looking for this degree of collapse between the omega and the beta phase, where you have the perfect omega phase, and here will be the beta phase, and also the competition in energy between those. You could see that if you change the amount of niobium in the system, then at regions above 11%, then you stabilize this beta phase. That is the one that you would like to go. Now, you also look for the one for the competition between the beta and the alpha phases. This is you calculate the Gibbs free energy. And you see as well that you will increase the amount of niobium, then you have a higher niobium composition, goes to lower beta transition phase between the alpha and the beta phases. Now, with that, you could see that this amount of niobium will be interesting in order to stabilize the system. As well, you have to see if how is the elastic property. So this here I'm going to show you a two-dimensional information for the elastic moduli with increasing niobium content. In summary, what I can give more detail later, but in summary, you could get a best composition based on the elastic properties. So basically, the information is that for the contents with niobium above 11, you have a good candidates for the bonding implants. You figure out the special compositions, and you calculate the full elastic properties of that. And finally, of course, you have some differences between the machine learning and the dysfunctional. This is expected, but they still are in a good shape compared with the experimental part. So this means that these compositions can be a potential for alternative for TNZT as a standard material. Now, this is very interesting because in the end, you could figure out a nice composition that gives to us good elastic properties. Now, to the end, then you have applied that for implant models. So you have usually actually a bond and try to see if you have fixing a plate on this bond, how is the effect of that? As well, you have this model for the hip joint implant model, where you look at how is the response of those systems regarding to the elastic properties of the bonds, as well as the alloy properties that you have figured out together with the reference one that is usually commercially nowadays. So just to give you an idea about how is the effect of that. So here's the stress distribution for the implants. So you are talking about this region of the bone, and you have this plate that fix these two parts of the bones if you have a fracture. Now, if you compare the stress response of the alloys that you figure out together with the reference one, basically you have a very similar mechanical behavior. So, and also it's I mean, the performance compared with the titanium alloys is much better. Now, you also, this is the example for the other model. You have a similar result. So basically, compare with the reference one, the stress, here is the von Mises stress, is more or less, you have a very similar response from the mechanical point of view. In this implant, usually is put it here. And then you have this very complex combination that you have the interface between the bone and the implant. In those materials that figure out have a good response. Now, just as a concluding remarks, so the machine learning was able to capture the features, define a composition sweet spot, figure out a low modulus alloy. The ab-initio calculation allow us to explore the composition rates. So here in particularly, you see the importance of niobium to the structure and the electric properties. And you could get optimal ternary composition for those applications. And finally, the finite element simulations could allow us to explore real case systems, and you have a very good combination of the ternary alloys that you discover together compare with the standard TNZT alloy that you have it done. And basically, you didn't see any significant difference between the stress response between those alloys. So as a take message home, so this multi-scale approach allows to predict and also to propose a comparable material with the standard TNZT1. And now you are trying to see if you could synthesize those and make a real application. So with that, this has been shown on this paper. And finally, I would like to thank my team in Brazil, in particular, Daniela, Bruno, and Camilo for those, and the Brazilian funding agencies that support this work. And finally, thank you very much for ICTP for everything that has done to myself in my career. Thank you very much, Shobana. This is it. And I'm open for questions. Yeah.
Thank you, Kitano. There are actually several questions. I don't think we'll have time to take them all. Gianmarco Rignanese has a question. Gianmarco, can you ask your question?
Yes, I was wondering how you perform feature selection. And in particular, I was wondering if that's so important when you do a random forest.
So the one that you have in this particular case, you have done, you have used a set of around 550 features that it was available for those materials. In this particular case, you have used this Keras library to make this selection. Now, regarding to the for the random forest and the other methodology that you have used, so what you would like to see here is actually how robust was this particular region that you're looking for. And in this way, you have done first with the random forest and see, I mean, the amount of the error that you have there was good enough, but you try a completely different way. That was the neural networks, and this part that was the one that was robust for us. Now, for the it was interesting to see that for the different cases, several of the properties that come out as good descriptors was more or less the same.
Okay, maybe you partially answered his question, but Nathan Daleman has a question. Can you ask it, please? Hello, are you there? Yeah.
Yes. So it's actually on the same slide. So I was wondering where the what causes these differences between the random forest and the neural network on slide 9, where you were showing the comparison. So in the region that you are interested in, they give quite similar prediction, but then outside of these regions, is this due to the feature selection or due to something else?
So we imagine that, yeah, you imagine, I mean, that this may definitely due to the feature selection that was not exactly the same that you have obtained both. However, for the particularly the general response was more or less a similar one, and you have been very much interested on this particular region here. That was the one that called us the attention. It's supposed to be the ones that could have a better applicability for our applications.
Mm-hmm.
But
okay.
the fine details, yeah.
Which
okay.
Okay, yes, I'll yield the time.
Okay, we're
No,
sort of running behind. Yeah.
No, I just commented that I can write in the chat the final details about why.
Okay, we're running behind time, but maybe I'll just allow one last question. Hannah Rubin, can you ask your question, please? Hannah Rubin,
Sir,
are
I
you there?
see. I saw it. Yeah, I'm there. Can you hear me?
Yes.
Ma'am, can you hear me? Yeah.
Yes, yes.
Thank you, sir, for the nice presentation. Sir, I just want to know, in your slides that you have shown, you have calculated the role of the p valence electron, but for the transition elements, the d valence electrons play a vital role in because of their hybridization and the elastic properties. So I just want to know what is the role played by the d valence electron in this case.
So the d valence was part of it, but as you can see here, it does not come out as the really compared with the other features that remember. One thing that we are very much interested here is to have a model based on composition only for the elastic property. So even it can be an important feature for the electronic point of view, for instance, but this, in this particular case, where you're looking for the elastic properties, it does not come out as the one that is relevant compared with the other one. I don't know if
yeah.
Okay.
I think we're out of time. There are many more questions, many more raised hands. So I'm sure Caetano would be willing to answer if you were to approach him.
Definitely,
offline.
yes.
Okay, thank you for a very interesting talk. And we'll move on to the last talk in the session. This is by George Dungich from the Tyndall National Institute in Ireland. And the title of his talk is Lattice Thermal Conductivity of Highly Anharmonic Materials Beyond the Boltzmann Transport Approach.
Hello?
Yeah.
My name is George Dankic, and as you said, I'm calling from Tyndall National Institute in Cork, Ireland, and I'm going to present fairly new method of calculating lattice thermal conductivity of highly anharmonic materials, which goes beyond the standard Boltzmann transport equation approach. This work was done in collaboration with Ulla Hellman from Linköping University under supervision of Ivana Savic and Stephen Fay. A quick overview of the talk. First, I'm going to introduce some relevant quantities that will facilitate the discussion in the rest of the talk. Then I'm going to outline the derivation of this new approach for calculating lattice thermal conductivity, which I will call Green-Kubo approach. Then I'm going to present results for germanium telluride and explain them using vibrational properties calculated from this Green-Kubo approach. In the end, I'm going to conclude by summarizing results presented in this talk. There are many reasons why one should be interested in modeling lattice thermal conductivity. For our group in particular, we are interested in improving the thermoelectric efficiency of the materials, and one of the most promising ways of achieving that is to reduce lattice thermal conductivity. 4,6 materials are one of the most promising thermoelectric materials, mostly because of their low lattice thermal conductivity, which is a consequence of them being close to the structural phase transition. This proximity to the structural phase transition makes these materials extremely anharmonic, which limits their phonon lifetimes. Additionally, this anharmonicity causes phonospectral functions in these materials to exhibit exotic behavior. For example, in lead telluride, experimental results showed that the phonospectral function exhibits double peak structures rather than expected one peak structure. In this talk, I'm going to focus on germanium telluride, another example of the 4,6 materials and promising thermoelectric material that undergoes a structural phase transition from rhombohedral to cubic phase at 600 to 700 Kelvin. There are many ways of calculating lattice thermal conductivity from first principles. For example, one might run molecular dynamic simulations and then use Green-Kubo relations to connect fluctuating heat currents and lattice thermal conductivity coefficient. Alternatively, one might use phonon dynamics, or some people call it lattice dynamics approach, to extract the relevant phonon properties, then use those phonon properties in Boltzmann transport equation, usually in relaxation time approximation, to extract lattice thermal conductivity. Boltzmann transport equation sees phonons as a gas of weakly interacting particles that carry heat between scattering events that happen every phonon lifetime. How do we use Boltzmann transport equation in practice? Well, we first calculate vibrational properties of the materials from the density functional theory, and then using, for example, the temperature-dependent effective potential method, as we did in our case. Of course, this method, Boltzmann transport equation, and also the method that I'm going to show later on, are not only viable with using this method of extracting vibrational properties. You could practically use whatever you want. So what we do is we expand the material Hamiltonian in the Taylor series with respect to the atomic displacement. The coefficients in this expansion are called interatomic force constants. For example, the second order interatomic force constants give us harmonic phonon properties, such as phonon frequencies and group velocities. Third and higher order interatomic force constants give us phonon self-energy, which measures the interaction between phonons. This phonon self-energy is a complex function of frequency for each phonon mode. The imaginary part of phonon self-energy gives us a phonon lifetimes, as shown here. Then we use these properties calculated from first principles in the Boltzmann transport equation expression that I showed in the last line here to actually calculate the lattice thermal conductivity. Here, just to note, this N denotes the phonon population at certain temperature, which is calculated as a Bose-Einstein occupation factor. Another property of interest is the scattering cross-section, or the probability of phonon to interact with a probe, which can be neutron or light incoming in the material. This scattering cross-section will be proportional to the spectral function, which is a Fourier transform of the displacement autocorrelation function. The Boltzmann transport equation assumes that the spectral function takes a form of a Lorentzian function, which means the imaginary part of the self-energy is constant with respect to frequency, and the real part of the self-energy is zero. However, we can calculate the spectral function directly from the perturbation theory, and we get a bit more complicated expression. But the most important part to note here is that the self-energy, in this case, imaginary and the real part, are the function of frequency. So how do these two expressions compare for highly anharmonic materials? I'm showing that on the graph here. So I calculated phonon spectral function fully from first principles and the perturbation theory, and I'm showing that in the red line here, while the blue line shows what Boltzmann transport equation thinks the phonon spectral function looks like. And we can obviously immediately notice the stark difference between these two lines. This difference led us to question the applicability of the Boltzmann transport equation in modeling lattice thermal conductivity in highly anharmonic materials. So what we want to do is to include the entire information from this phonon spectral function in our calculation of the lattice thermal conductivity. How do we do that? So, well, we start from the green cubo expression for the lattice thermal conductivity. Here, kappa is the lattice thermal conductivity, and V is the volume of the simulation cell. T is the temperature, Kb is the Boltzmann constant, J is the heat current, and the brackets here mean the heat current gets autocorrelated. First, what we have to do is to define a heat current J. We use the definition of the heat current shown here. People who are calculating lattice thermal conductivity from first principles will notice that this definition is different from more commonly used parallels one, which defines heat current through the phonon population operator. But one can show that the parallels definition of the heat current is an approximation of this expression. Another point I want to, another detail I want to point here is this quantity VQSS prime, which is a generalization of the phonon group velocities. The S and S prime are the phonon branches, so this goes beyond the standard definition of the phonon group velocity to include the off-diagonal terms in the group velocity matrix in the phonon eigenvector space. The A and B operators can be defined in terms of the phonon creation and annihilation operator, as shown in the last line here. Once you go through whole derivation of this expression, you end up to expression like this one, shown in the first line. Important thing to note here is that we have an integral over the frequency range. And under the integral, we have what we can see, what we can recognize as the phonon spectral function. So we did include the entire information of the phonon spectral function in our calculation of the lattice thermal conductivity. Another important point to note here is that the summation here goes through two branch index, S and S prime. So we can split this expression in two parts. The first part is diagonal in phonon branches, which is the traditional definition of the heat current. And the second term is non-diagonal in the phonon branches. One can show that the diagonal part, so when S is equal S prime, in the limit of the low anharmonicity, that means that imaginary part of the self-energy is much smaller than the phonon harmonic frequency, and the real part of the self-energy is zero, that this expression reduces to the Boltzmann transport equation in the relaxation time approximation. The non-diagonal part has been already described in these two recent publications as the primary transport mechanism in amorphous materials. In the previous formula, it has a slightly different expression, and we can note that the non-diagonal part gives contribution only if there is a substantial overlap between two spectral functions of phonons with the same Q vector but different branches. And here I'm showing the overlap of the spectral functions of two soft modes in germanium telluride close to the phase transition. And we can see that the overlap is only for the low frequency region, so that only the low frequency region will give contribution to the non-diagonal part of the lattice thermal conductivity. Now I would like to show the results for germanium telluride. First, I'm showing the relative difference between results obtained with Green-Kubo method and results obtained with the Boltzmann transport equation. We notice that the Boltzmann transport equation consistently underestimates the results from the Green-Kubo method. We can also notice that this underestimation is not large. At most, it's around 14%. We also notice that the difference scales roughly linearly with temperature, which we might expect because phonon self-energy scales roughly linearly with temperature. Also, the difference peaks at the phase transition, which is also understandable because we expect germanium telluride to be most anharmonic at the phase transition. If we split this difference coming to parts that come from diagonal and non-diagonal part of the lattice thermal conductivity, we can see that they are roughly equal in germanium telluride. One has to keep in mind that germanium telluride is fairly simple material with only 2 atoms per unit cell. We expect in more complex crystals that the non-diagonal part will be much more prominent. So why is there increase in lattice thermal conductivity?
Excuse me, you have 5 minutes left.
Okay. Why is there increase in lattice thermal conductivity going from Boltzmann transport equation to the Green-Kubo approach? One can look at it by mapping the Green-Kubo expression to the Boltzmann transport equation expression to extract phonon lifetimes. If we do that, we calculate the phonon lifetimes in Boltzmann transport equation and the phonon lifetimes in Green-Kubo method as defined here, and we find that the phonon lifetimes in the Green-Kubo method increased substantially, especially for the region of the soft modes. Well, does that make sense? Intuitively, it does not. And if we look at this phonon spectral function, we can see that the Boltzmann transport equation spectral function has a smaller line width than the Green-Kubo spectral function. This means that one should expect higher phonon lifetimes from the Boltzmann transport equation than from the Green-Kubo, which is not in accordance with the previous picture. To analyze this more deeply, we Fourier transform our spectral function into time domain to get a time-dependent atomic displacement autocorrelation function. And we showed this for two temperatures at 300 and 631 Kelvin. At 300 Kelvin, we get expected behavior for weakly anharmonic material, relatively weakly anharmonic material, where we have oscillations and overall decay of the correlation. However, at 631 Kelvin, the anharmonicity is so strong that we do not observe any oscillation at all and only have the phonon, the decay of the autocorrelation function. We can fit these two behaviors to the damped oscillator function to extract what we usually associate with phonon lifetimes and frequencies. If we do that and we plot the fitted lifetimes as the red points here and the Boltzmann transport equation lifetime as the blue points, we can see that the fitted lifetimes are indeed smaller than the Boltzmann transport equation lifetimes, which is in accordance in our with the spectral function graph. So why is there an increase in the lattice thermal conductivity then in the Green-Kubo approach? We explain that by extracting the anharmonic phonon populations from the displacement autocorrelation functions. And we can see that anharmonic phonon populations mostly increase in the entire frequency range, and most prominently for the phonon soft modes. So we can say that the increase in the lattice thermal conductivity that we observe in the Green-Kubo approach is actually due to the increased phonon populations. Why do phonon populations increase? We understand that from the plot of the frequency shifts between fitted frequency and the assumed harmonic frequency in the Boltzmann transport equation approach. And we can see that the phonon softening due to the phonon-phonon interaction causes anharmonic phonon populations to increase, which increases the overall lattice thermal conductivity. We started this investigation because we wanted to make sure that our results for germanium telluride close to the phase transition make sense. And we already proved that, because the difference between Green-Kubo approach and the Boltzmann transport equation approach are not very big. It's around 10%, which is way less than what you would expect from the variance in experimental results, which are shown in this figure here as the gray region. But it is hard to gauge the predictive power of this Green-Kubo approach due to other effects that influence lattice thermal conductivity in germanium telluride much more, such as, for example, vacancy scattering. The predictive power of this method might be better tested in more complex materials with more atoms per unit cell that exhibit the amorphous-like lattice thermal conductivity. In the end, I'm concluding by saying that we presented a method for calculating lattice thermal conductivity of highly anharmonic materials based on Green-Kubo approach. This method incorporates information from the entire spectral function of phonon modes. In the case of germanium telluride, Boltzmann transport equation underestimates the lattice thermal conductivity compared to the Green-Kubo approach. The reason for the increase of the lattice thermal conductivity in the Green-Kubo approach with respect to the Boltzmann transport equation is due to the increase of the phonon populations due to phonon-phonon interaction. The more details about this approach and in general the lattice thermal conductivity in germanium telluride can be found in this archive link here. Thank you for your attention.
Thank you for a very nice talk. There are several questions. I think we have time for maybe one or two. Yuhit Gupta, do you want to ask your question? Yuhit Gupta, are you there? Okay, let me ask the question. The question seems to be, our calculations of lattice thermal conductivity by using Slack's equation not accurate enough to give exact results, accurate results?
I didn't hear the question at all.
Okay, sorry. Can you hear me now?
Yeah. Yes.
So the question was, are calculating lattice thermal conductivity by using Slack's equation not accurate?
Slack's equation?
Yeah.
I'm not familiar with the.
Okay, I'm not either, so I can't
actually.
help you. Yuhit Gupta, are you there? Can you elaborate on your question? Okay, somehow all the questions seem to be from India. Pankaj Kumar Gajjar, do you want to ask your question? Pankaj Kumar Gajjar, are you there?
Yeah, I am
Can you
here.
ask your question? Can you ask your question?
Yeah. My question is, okay, while calculating the lattice thermal conductivity, why in most of the cases we ignore the electronic contribution?
Well, there is two good answers to that question. The first answer is that, well, in the modeling of the thermoelectric properties, the lattice thermal conductivity is somewhat decoupled from the electronic properties of the material. So you want to reduce lattice thermal conductivity without actually reducing the electronic properties of the material. Specifically in the case of the germanium telluride, one would expect for very low doping that the lattice thermal conductivity will be the dominant factor in the total thermal conductivity. So that's the reason why we not considering the electronic part of the thermal conductivity in this work.
Yeah, and is the same is true for electrons?
Can we move on to the next question, please, because we're running out of time? Natalie Vast, do you want to ask your question?
Hello, do you hear me?
Yes.
Yep.
Yeah, thank you very much for the nice talk. My question was about the fact that in your lattice thermal conductivity, the new expression, you neglect probably the fourth order anharmonicity in the frequency shift. And I was wondering whether you believe that this could be an explanation for the high value of the lattice thermal conductivity. And in particular, do you expect that it could explain the big difference you find in the cubic structure?
Yep. Yeah, I understand the question. So if I go back here, well, in this method, it doesn't really, you don't have to stop at the third order anharmonicity. You can go in the expansion of the Hamiltonian to whichever order you want. Your expression for the phonon self-energy is going to get a bit more complicated, but this method is not constrained on using only third order anharmonicity. So that part of the question, I think, is answered. The other part of the question is the fourth order anharmonicity, the reason why our results are so different from the experimental one in the cubic phase. I'm not sure if that's true. We calculated the fourth order anharmonic force constants, but we found that they, in the lowest approximation, do not have a large influence on the phonospectral functions. So it's either the lowest approximation is not sufficient in this material, or the fourth order anharmonicity is not relevant. So it's inconclusive. We don't have a conclusive answer to that question, but it is a very good question and worth exploring further on.
Okay, thank you. Unfortunately, we have to cut the discussion short because we have to wind up. I thank all the speakers and I thank all the participants. We have continued to have a very large number of participants online. I thank everyone for their interest lots and lots of questions, and I can see that a lot of the questions are from students, and I congratulate them on their curiosity and their enthusiasm. I thank the organizers for inviting me to chair this session, and I hand over now to Nicola in case he has any announcements.
Thank you. No, I don't have any announcement. I think we can go to the coffee break, and then in 10 minutes we can meet again in the poster rooms. So see you later and see you tomorrow at the same time. Thank you.